Hey gang, how you guys doing today? Happy Tuesday. Alright. Well, I think things are looking good. The Comcast has been a mess lately, which is unfortunate, but hopefully it's stable today. Hopefully you got your coffee, just had some lunch. It's a late lunch, it's okay. Got some coffee. Alright. Yeah, I think I gotta set up a second computer again to do this Stream Manager stuff. Like, mine's just getting sad at just about 2 years old now. But that's okay. Can make it work. Hopefully it's not too bad. Let me know if it starts lagging a lot, and I'll make some adjustments if needed. So we are moving on to our next topic, and we're going to talk about recursion. So we're going to do recursion as our first individual project of 4 is the plan for this. We're going to talk about recursion today. We'll talk about recursion Thursday, and I think it's probably better to wait till Thursday to talk about the project. I probably can today if you guys want, but Thursday, might be a little bit better after we've had a little more time to cover recursion. So if you were with us last semester, we touched on it briefly. So we're going to do a quick recap on that and then dive a little deeper into some of the interesting pieces here in recursion. And this is super important because we're going to use recursion later on in data structures once we get to trees and queues and stuff on from here. Okay, so it's an important topic in algorithms and data structures as well. But you can do some cool stuff with it. You can solve some nice problems. So let me fire up a PyCharm project here. Make sure my GitHub repo is up to date. Oh, and then we're going to talk about the lab today. That's right. The lab from yesterday had a couple questions, so wanted to go over that again. The goal for labs is you guys get it done. I know we had Git was new, and then we're doing some stuff with classes and inheritance, so that's okay. Let me pull this one here. Yeah, I started up an example project. I was sending people some screenshots here, so I'm just gonna, if you don't want the changes here in Git, you can say discard, which is a little bit dangerous, so just be careful because it will delete files. So anything that's new, if you discard it, it just goes and deletes the file and says, oh yeah, you're about to lose them here. Yeah, I want to discard them, which is fine because it was just an example project. I didn't care. There we go. All right, things look pretty stable here now. You guys doing all right today? I think PyCharm was loading behind the scenes somewhere. Yeah, all right. Maybe? I don't know. I think my computer needs a full reload. I'm scared to reload it during the week and have it break. Let's see. Come on, Task Manager. What do we got? Do we have PyCharm? Nothing? We just have it being sad. Oh, there's PyCharm. Okay, it is trying. It's okay. We're getting there then. Discard one more time. Come on, discard. It's trying to reload it. Cancel. Don't open the project. That's why. I deleted the project as it was trying to load it. That would make me sad. All right, they were fighting each other now. Yeah, definitely an abstract-based class. We'll talk about that. Okay, I killed PyCharm by mistake. Come on, PyCharm. It's not PyCharm's day today. Just close that. See if I can save some. Come on. Give me PyCharm. Let me close this one down. Don't need that. Any day now. For the R value, I mean, I wouldn't expect a fraction, but like a decimal, I think would be expected, especially if we're looking for a number less than 1. Definitely think fraction there makes sense, or a decimal makes sense. Ooh, a dad joke. All right, I got a couple good ones for you guys here. You know, I was going to start a new club on campus for Apathy Anonymous, but I figured why bother? Maybe I can get PyCharm to load. Killing me here. Kill that one. Got nothing. No, I don't think we need to do any special error handling. The idea of the practice here was just for just using the classes and doing that inheritance stuff. Yeah, just ask for the number, and we can assume they'll give us the right thing. Calculator is open. Why does PyCharm hate me? Wonder if it's actually running and it's just not. Yep, so it is. It's just dead. So let's end the task and try it again. Maybe now it'll run. There it goes. It was just like a zombie process. It's one of those days today. All right. Okay, new project. So let's talk about lab 0, right? That was lab 0, I think I called it. Probably have that back open again. I closed it. That was silly. All right, assignments. So I think I made Git repos for everybody who wanted one. If you didn't get it, let me know. I can definitely make your repository. Okay, there we go. So basically this was copying, part 1 was copying from the textbook. So if you don't mind me, I'm going to cheat here and copy from myself, because we did this last year. So no surprise. And I think, oh, is that public? It might be. Let's see. Maybe it's in here. Regression. I think it's in this repo. Nope. I spelled it wrong. Regression. Is it not in the repo? Now I'm sad. Nope. I know I had it in here. I thought I did. Is it the year before? I'm going crazy now, folks. I just don't want to have to copy it out of the book. It's tedious. Come on. There we go. Okay, I do have it. Good. So again, if you're going to copy stuff out of GitHub, you want to use the raw button. Okay. So I'm going to add a new file. Again, I like them all in one class per file. That's just me. Other people don't, and that's okay. Not a big deal. So don't sweat it either way. Oops. That should be progression. And let's see what else we had. Is that it? Oh no, I put them all in one. Oops. Yeah, progression, arithmetic progression, and geometric progression. Sure. Let's make that a little bit bigger. Is that easier to see on the eyes there? All right. Sure, we can have them all in one. So the idea with progression is it's just going to add one at a time with this private advanced method here. And then this iter here is this special method saying, hey, this is iterable. It's an iterator. We can iterate over myself using a next. So as you're iterating over something, you ask for next, you ask for next, you ask for next. Eventually, you'll stop. And then you're done. So when we start off, we're starting at 0 by default, unless we give it something else. So this is a base class. This one's not abstract. So this one has everything in it defined. It can do everything all by itself. If we wanted it to be an abstract base class, we would take out the definition for advance and say, oh, I'm not going to define it. You wouldn't be able to use it as an iterable as easily. There's ways you can call next, but like using it in a for loop is essentially calling next here. So in main, if we're going to go, let's zoom in here. Let's dump all that. So if we were to import regression, and then say, you know, for n in range 10 something or other, we got to make a progression. So it's progression. So if you don't import specific classes using the like from progression import whatever, it's progression dot. So module dot class name here. Like, sure, the start was 0. That's fine. So this is our first progression. And then inside of here, I could print. Oh, I'm sorry. No. Because we want to loop through it. That's right. So we'll say for value in first progression, print value. So we can just iterate over it. And then in here, I'm going to keep a count just for fun. So count starts at 0. We'll say count plus equals 1. And if count is greater than, or I'll say equals 100, we'll break to stop the loop here. This way I can just iterate over the first progression. And if we put this in debug mode, we can watch it happen here. So we're going to debug this, and we'll step into first progression here in a second. Okay, so we have first progression, and now we're going to step into our code. So the first thing it does is it returns it as an iterable because we're using it inside that for loop. So when we say for value in first progression, it has to get the iterable piece of itself. Then we can iterate over value one at a time. We'll step. Now we go to next right away. So the first thing it did was get it, and then we're getting the next value as we're assigning value. Okay, we advanced. We got a 1, and we're going to print the value. So 0. There's the first one. Now we go immediately to next, because we're just asking for the next value, asking for the next value, asking for the next value throughout. Does that make sense here? So the iterator is called initially using it in the for loop. So if we don't have it here, if we were to just comment that out, should be unhappy with this here. Yep. The progression is not iterable. So we can't use it in a for loop. Does that make sense, Eric? I'm going to uncomment those out. Then if we just run it, we should get 0 to 99. Cool. It's our basic progression. Yes, debug is fantastic. We'll use the debugger a lot. So in the printing itself, this is this list comprehension syntax, which is awkward and weird. So we're saying you kind of read it backwards. So instead of having a for loop with something underneath it, you have a for loop and then the thing you're doing over here. So what it's doing over here is it's getting the next. So you can ask for next as well if you want. So iter just means it's iterable, so I can put it inside a for loop. You can also say, if we wanted to do this alternatively, let's have second progression. Progression equals a progression dot progression. Sure. And then we'll say for n in range 100, print we want next of second progression. So next is a special keyword. That means give me the next thing. And let's debug this one. So we step into our code. Right away, we just jump to next. So we're not using the iterable. What iterable lets you do is put it inside of a for loop, which is essentially doing this exact same thing, where it's saying next. So this exact same for loop is pretty much the same thing, where next is getting assigned to value, but this one's never going to end. So what we did here, using a controlled range loop, we're only doing it 100 times without having to break. And we should get the same results. If I take the breakpoint off and continue, we should get our same values. 99 again. All right, so here's the first to 99, and here's the second to 99. We've done the same thing, essentially, with a different progression. So this one is calling next, asking for the next value in the iteration. This one is using a for loop because it is iterable. So in this case, I'm pretty sure, actually I haven't tried it, I know I'm curious, if we comment that out, and we got to comment this out, oh boy, it's the triple block, is that it? Triple block, there we go. Triple apostrophes is like a comment block. You can do other cool things with it, but so if I leave out that first one, we want to see, can we use next in second progression? Oh, expected something iterable. It might not work. No, it did work. Okay. So it warns us and it says, hey, this thing doesn't iterate. It's not iterable, but it still works because we have the next method. So that's kind of bad form, though. Let me undo some of those changes here. Okay. So it's just using the iteration one way or the other. We okay with that so far? So part one, again, just copy paste, essentially. Progression, arithmetic, geometric, and Fibonacci. Did I have all those in here? I think I did. Yep. So then we have an arithmetic with a start and an increment. We have a geometric, which is the base, and we have the Fibonacci. Okay, so just grabbing all those. So looking around at each of these, right, they inherit from progression. And what they do is they override the behavior to make it special. So what makes an arithmetic progression special is the constructor. It still calls the superclasses init method, giving a starting value, but it has its own init. I'm sorry, I'm kind of far away from my camera here. My back's bothering me, so I'm just kind of leaning back. And it sets an increment. Then when it advances, so we're changing how advance works as well. So we have our own init, which still calls the superclass init, and then we have a different advance. So advance changes by the increment instead of +1. So next still does the exact same thing. It calls advance on itself each time. It's still iterable, and it still prints the exact same way. But what's special is the advance method that's called inside of next, you get the correct version. Same with geometric progression. It's a progression, but now advance is multiplied by the base. And then Fibonacci is just different, right? We're going to start off at 0, and then we have a previous value, and then we advance as temp, previous, and temp plus previous. The book does this differently, and I'm always confused by that notation. You can assign multiple values at once in Python, and that just hurts my head. So I did it in 3 lines with a temp. So if you notice that's different than the book, that's on purpose. Sorry, what is going on with my sugar here? Oh no, that's going up too high. All right, let me grab this real quick. Here it is. Sorry, I'm a big fan of modern medicine. So insulin stuff is amazing, even if it is expensive. It's still good stuff. I mean, it's worth it, right? Okay. All right. Yeah, this little pen, this thing's awesome. All right, so we were going to do a couple things now. We did part 1, we copy pasted. Now we're going to come back and do part 2. Part 2 says, using the geometric progression, we're going to write a script that verifies if we have an r of less than 1, that the sum approaches 1 divided by 1 minus r. So allow them to use an r value, make sure we use a float, and then run it until we're within some value of the calculated sum, outputting the current sum in each iteration. So if you haven't taken Calc 2 yet and done sequences in series, this is a series. A geometric progression is a particular kind of series where we can calculate the sum, which is pretty cool. Okay, so we'll have all that. So then we'll ask the user to enter an R value. So we'll say, I don't know, R value is an input of, please enter an R value between 0 and 1. And then we need to make sure we convert all of that to a float, right? And then we'll give that R value to our geometric progression. So geometric progression equals my progression module. Oops, progression module.geometric progression given my R value. Okay, and then what we're going to do is we're going to have a sum, right? Starts off at 0, and then we're going to loop. We're going to say while sum, I guess we should have an expected, and we'll have an expected sum is 1 divided by 1 minus the R value. Okay, and we're going to say while, and probably easier to use the absolute value here. Is it fabs? No, fabs. Fabs is C++. The absolute value of the expected sum minus the sum is greater than 0.00001, right? Or whatever value we wanted here. It doesn't like my white space. Is that an absolute value? Oh, okay. Redundant parentheses. Thank you. So while the absolute value is greater than this, so while the difference is bigger, right, we're going to keep on doing this. So we're going to take my sum, and we're going to plus equals the geometric progression, the next, right? Next geometric progression. We're just going to keep on going, and then we're going to print the sum. Okay, so it doesn't like me using the word sum because that's the built-in function sum. So sure, we'll call it current sum. And I'll copy paste that a couple places here. Current sum. Okay. So let's try it. All right, so if I use 0.5, the idea here with the geometric progression is we start off at 1, and then we keep multiplying by 0.5, by 0.5, by 0.5, by 0.5, by 0.5, by 0.5. So we should get 1 plus a half, plus a quarter, plus an eighth, plus a 16th, plus a 32nd, plus a 64th, on and on and on and on. That sum should approach 2, because 1 minus a half is half, and 1 divided by half is 2. Right, that's what we should get, right, given 0.5. And we'll see, after so many iterations, we get 1, 1.5, 1.75, plus an eighth, plus a 16th, on and on and on. Eventually, we get close enough that our delta here, right, is small enough, and we say, good, we're close enough. Does that make sense? So let's try this again. We'll give a different value. So let's go with like 0.99. It takes a lot of iterations to get close enough. Look at that. Woo! That's a bunch. But it does it pretty quick. Eventually we get there. There we go. Right, so starting off with 1, and then 0.99, 0.99, again. How you run and debug. So for a debug, over in these line numbers here, there's like a big gray space. You just click in there and it drops a big red dot. That's called a breakpoint. And then when you right click, instead of run, you use debug. And then it's going to stop the execution. And then you get some cool buttons here for step. So R value, let's say 0.5 again. And I can see all of the variables. Unfortunately, this I can't zoom, I'm sorry. But you can see all of the variables and their current status or current value here in the debug menu, the debug console. And then most of the buttons we use are step into my code or step over or step out. So step into my code means if we're doing something in our code, let's go into that method, into that function. Here, step over means go to the next line. Right? So step over will take me to the next line here. If I don't care about next, I can just step over and I'll see now current sum is now 1. Right? And I can step over, it checks my while condition again, comes back here, current sum is now 1.5, and on and on and on. So, yeah, we can step into. So if we step into, it'll go into our next function here. So don't use the step into, use the step into my code, because you can get into the Python libraries and they're just really confusing and it's not helpful. We want to step into our code, which will take us to the next function. So next now, when we jump over here into progression, we now see self. Self is the geometric progression with a base of 0.5 and a current of 0.25. And then we can step in here. We'll see, okay, we have an answer. We're going to advance. So I can step into advance, which will take current times the base. Okay, so we'll get a half of a quarter. Should change my current now to an eighth, 0.125. And then we're going to return answer. Hey, Professor Peter and Math Company. Welcome, welcome, welcome. We are having fun with sequences and series, actually. I did not plan this. I did not plan this. So we're just going to keep on printing that current sum as we go to see if we can approach the expected sum of our geometric progression. This is fantastic. I should have you take over. Can I get you on Zoom here real quick? I'm only partly joking. Okay, so we can see that if I just continue this on here then, right, we'll go continue and come back to my console. So there's the debugger tab and there's the console tab. Here we'll see the current sum as we do each iteration of our geometric progression, adding to the existing sum until we get close enough to that delta. We'll have to plan that sometime. That would be a lot of fun. That would be a lot of fun. So we can try it with different R values. Do you have a suggested R value for our geometric sum? Let's try it. I think it works with negative values too, isn't it right? Is it the absolute value I think works? So if I do like negative 0.5, yeah, look at that. It does work. It does. So, okay, so we want between -1 and 1. And between here is key. If it's 1, right, we're going to sum to infinity, because 1 times 1 times 1 times 1 times 1 times 1 times 1, if we add it up, will be infinite. And we'll just make Python sad here. Okay, but for now, right, 1 minus a -1/2 would be 1.5, right? And 1 divided by 1.5 is 0.666666666 continuing forever. And we get 6666666 continuing until we hit our delta. So we can have fun with this little simulation here. So are you making sure you're adding to sum here? So you should have a value like current sum, and then you add to the current sum, giving the next value, and the next value, and the next value. What part of that would you want to write into the class, Eric? Like this, the checking the value here? Okay. Yeah, and I'll post all this code for you guys when we're done. Don't worry. Like, you're welcome to try and follow along as we go and shout at me. But that's all good. But I'll also post it when we're done. I know it's the lab exercise, but you're welcome to cite my code on GitHub for the lab exercise, and we can go from there. Yes, we ask for input. Well, so summing the geometric series, we could add in a sum here. Like we have a print. We could add, like return the sum of n values or something like that. It sort of depends what you want to do. You got lots of options. Yeah, for sure. I mean, we're printing it here, so you can just return it as a list, right? Just take for value in range n. Definitely. I should do that. Let me do that right now. Look at that. You guys are amazing. It's my Nightbot. Let's see. Log in with Twitch. Come on. I've been in here before, Nightbot. Why are you so confused? Yeah, we can take a look at it after, too. We can chat on office hours after. I'm sure Nightbot is trustworthy, right? I didn't even read any of that. setting such a great example. So let's add a GitHub command. Check out all my code examples on GitHub. Oh, it already exists? Did I already do that? It already. There's already a command. Oh, that was a big fail. Yeah, exclam GitHub there, and you can see the code. I apparently had that good idea already. I had it already. So that was part 2, our geometric progression. So you can have different R values for geometric progressions, they just don't sum, which is okay. Right? This is just an example here. You'll run into calculus class, and you'll remember that this was cool. Which I'm told, I don't actually know for sure, but this was a rather trustworthy source, is that this is how it works in your calculators. Right? It does this exact sort of thing, given whatever built-in delta that it has when it does series and sums. So and I did, what was it? Calculator foundation. He posted about a new calculator that's cheaper than TI-83 and has a built-in Python. Where was it? Calculator alternatives. I'm sure I'll find it here somewhere, right? Come on. Okay, let's go to Twitter. Hanselman. I know it's on here. This is worthwhile because the calculator has a built-in Python prompt, and that's like the coolest thing. I just need to scroll down. This guy tweets a lot. He's awesome, by the way. I know, a calculator with and it's approved for the ACT, SAT. Come on, let's get this to load faster so I can do a Control F. Can I search him and calculator? Does that work? Oh, come on. That's Hanselman calculator. We'll see if that works. Calculator. This one, yeah, num works. Here we go. So num works. Calculator. This thing is awesome. I checked it out. I almost ordered one, but I don't actually need one for any reason, so I didn't really want to spend $100 on it. But check this out. This calculator is awesome. It has an emulator. Oh, come on, where is it? It had all these cool things. Apps. Built-in Python. Although I wouldn't recommend having to type things using the calculator, but that's okay. But you can do little Python stuff. It can do graphing and stuff built in. Like, check out how cool that is. Can add systems of equations. Yeah. Look, you can do sequences, you can do regression. Like, I was drooling over this calculator, which is ridiculous. But they have the emulator, and you can just use it online too. I don't even have to pay for it. Free online version. Look at that. What were we doing? I'm sorry. I got excited by a calculator. Okay, we're back to our lab. Oh, this last one. Part 3. Right? Use the Fibonacci progression to test the theory of number distribution and Benford's law. So if we take a look at Mr. Benford's law. Maybe if I get my computer to load. Numworks, that's it. That's the link, Numworks. That the first digit frequency, so the leading digit in many real-life numerical data sets, will have some sort of curve to it. Not exact, but this is what you're likely to see for your leading digit distribution. And we're going to check it and see, can we make that work? Okay, using the Fibonacci. So grab the first 500 values of Fibonacci, get the first digit of each, and I cheat by turning it into a string. Data values to span orders of magnitude. I don't actually know what that means. I'm sorry. That's okay. So we need our fib values, right? We need to get a bunch of these values out. So we're going to start it as a list, and then we're going to make a new progression. So this is my fib equals my progression class, Fibonacci progression. And we'll say for n in range 500, I want the first 500 values. Take fib values, and we'll just append next of my Fibonacci progression. Oh, yeah. Okay, so you need to make sure you're getting more than just values within 100. Yeah, for sure. Cool. So we've got this. Again, we could modify the code and do some sort of printing thing to make it prettier, but this is fine. Or we could just unsplit it and do it that ourselves. I guess we could do that. I don't know. This is probably fine because this is using the same syntax we did before. There's tons of different ways of approaching this. Sorry, I have to make sure my daughter's getting ready for piano lessons. She needs the computer. My wife is funny. She sent me this screenshot here for all my sports ball fans out there. It's Team Oxford, comma. It's totally me. All right, so then when we're done, just to see if we got our values out, let's just print our Fibonacci sequence, see if we can get all 500 values. Oh, an R value, sure. Oh dear. I didn't want to print fib. I wanted to print fib values. That's the wrong one. 5, sure, why not? Okay. So it looks pretty close, right? 1, 1, 2, 3, 5, 8, 13, 21, 34, on and on and on. That seems to be pretty good. So I have the values, okay? So, sorry, let me step out just real quick. I'll be right back. Let me put some music on for you guys. I had to go set up a Zoom session. I'm sorry. My wife's stuck with the little guy. Let's see what we got here. I think we did Final Boss before, but on a shuffle, right? Try this one. I'll be right back, sorry. So 4:15 p.m. I'll be right back. Just take a minute. Sorry, folks. No. Alright guys, I'm back. Sorry about that. Alrighty. Oh, that's why it was kind of quiet. There we go. Crank it. Alright. So again, we've got our Fibonacci values. Now we need to get the frequency of the leading digit. Okay? So to do that, we need to track the leading digit and then to count it. So we've done something similar like that before, where we used a dictionary. Right? So we had... what do we have? Like, we want to call it, I don't know, digit count equals a dictionary. Okay? And then we could set this up if we wanted here, or we could just go add a bunch of things to it. So I'm just going to say for digit in range, and I want to start at 1, and I want to go to 9, so I'm going to use 10 because it stops, right? I'm going to take my digit count, and I'm going to assign it. Oh no, I'm sorry, digit count key of digit, and then I'm going to assign it 0. So the key in my dictionary is the leading digit, and the associated value is how many times I've counted it. Right, so this will add 1, 0 times, 2, 0 times, 3, 0 times. So it's setting up my dictionary here. Again, there's other ways of doing this sort of thing. That's fine. I like this sort of syntax of thinking through it. Okay, so just setting up the dictionary. Then I need to loop through my Fibonacci values, and I guess we don't even need to save them in a list, right? We could just do them right in here. So let's do that. Let's cheat. So let's get rid of this fib values list because we don't need it. Okay, so now I want to say for value in range 500, we're going to take 500 values of fib. So we'll have a, and we don't actually care about value, right? That's going to be 0 and then 1 and then 2 and then 3 and 4, so whatever. We'll call fib value is my next of fib. And the problem is the first one is actually 0, which is unfortunate. So let me do next one time here. We'll go next of fib. Because I don't want to get back a 0, right? Because remember we start with 0 for our initial value, and that's going to screw everything up because 0 is not really a leading digit ever in anything. So get rid of the first one. Let's put a note. This removes or regresses past the initial 0 because I don't count that one. Is that okay? It's probably not math official, but that's all right. So we'll get the next value. Then I need to get the leading digit. So I need to turn that into a string of fib value. Once it's a string, right, then I can take the first position, the first character in that string. Then I can turn it into an integer. This is nuts, right? So I'm saying, hey, give me a string of the value, give me the first character, turn it back into an integer. Does that make sense? So I can do it more than one line. So this is the string fib value is string of the fib value. And then the leading digit is an integer of the string fib value, position 1 or 0, the first character. Is that better than a single line? That's a little cleaner here now, right? And now I take my digit count, key of the leading digit, plus equals 1. Add 1 to it. Right? This gets the value associated with that key in the dictionary, and it adds 1. So whatever that leading digit was, I'm going to now add 1 to the count in this associated dictionary. Right? And then when I'm done, I can print my digit count. You okay so far? Let's try it. Got too much of this other junk in here. That's all right. So here we go. Let's see. Did it work? So 1s as a leading digit was 151 times, and then 2 was 88. 63 times for 3, 47 times for 4, 40 times for 5, 33 for 6, 29 for 7, 27 for 8, and 22 times for 9. And that's all well and good here, but what if we wanted to plot that, right? What if we wanted to make this pretty? And again, this was above and beyond. We don't have to do that, but plotting is fun, right? So we're going to say import py plot. What was it? Shoot. I can never remember. I have to go. I'm just going to go plagiarize myself. You know what? It's not worth remembering. Eric CIS 1501 fall 2020. All right, this was last semester. We did some plotting here. I don't remember the names of what I'm supposed to import. It's not worth remembering, right? Not worth those brain cells. Where's our plotting? Plotting, there we go. This will give me the imports I need. matplotlib.py. py plot, that's what it is. Okay. And again, as PLT, I don't know. I guess people do that. The book did, so I just went after it. Sure. So PLT. So if we want to print that out, right, I can use, all right, what do I want to do? I want to plot, and I need to give it an x-axis and then a y-axis. Right, so x then is 1 through 9, or that's also my digit count keys. Right, and then the y is the digit count values. And then let's plot.show. I think that's it, right? Man, it's been like a whole month since I did this. Maybe a month and a half, right? R value, sure. Oh, that's right. We need to do this as a list, right? Because if not, the keys and values aren't actually lists, so it makes this thing awkward. Let's try that. One more time. There we go. And look at that, it plotted. That's kind of amazing, right? So here's our plot of 1, 2, 3, 4, 5, 6, 7, 8, 9. So the Fibonacci sequence follows the natural distribution of numbers, Benford's law. Right? And there's all sorts of other cool things here. Other ways of using Benford's law for other things. Not for everything, though, by the way. It had all sorts of fun stuff with election data recently. Tightly bound in range violates the assumption that the range data be large. First digits of precinct vote counts are not useful for trying to diagnose election frauds. This is Mebane. I don't actually know who that guy is. Let's see. 47. A fact check from Reuters. Reuters? Reuters. Reuters is just funnier to say. Let's see. So it's a red flag test. It can raise doubts. So the IRS uses it, but only implies it's not a guarantee, right? Then you audit and whatever. Here, professor in Department of Political Science, Department of Statistics at University of Michigan. Oh, he's local. Look at that. Authored an article on it, suggesting some limitations to the process. The test is worth taking seriously as a statistical test for election fraud. Okay, sure. On its own should not be considered proof that has occurred. I'm sorry, we got down a weird rabbit hole, folks. Are we okay so far? Let's bring it back. Let's bring it back in here. So that was lab 0. Okay. Bring it on back. So let me commit this to GitHub. We'll go save that. This is lab 0 now with plotting. Again, the plotting was extra, just for fun here, so we could see it visually instead of having to look at the data. All right. And push. Okay, so all that's out there in the GitHub repository in case you guys want any of that. Okay, so far? Let me start a new project. Do Recursion. Okay. So remember, we did have Fibonacci done without recursion here. Typically, when we talk about recursion, we look at how we can use a Fibonacci sequence, which is fun. We did that in 1501, and we talked about why it was a bad recursion. So we'll spend just a minute on doing that before we get into new recursion stuff. Okay, so the definition of recursion is a function that calls itself. That's recursion. So if I were to have a function like count given a number, we could say we'll print the number, and then we will call count of number minus 1. Call ourselves, and then we probably need a way to make this stop working. I mean, right now this is okay, right? I can call count and then give it 100, and this would work. That's a recursive function. The problem is it crashes because we got too far. There was no way to stop the recursion from happening. So it is recursive, it's just not good here. So what we do when we write a recursive function is we need to identify two things. Right? The first thing you need to identify is what we'll call the base case. What is the simplest way, or what is the solution? Can I find a solution here? Right? How do I know when to stop? So for us, we're going to say if number is less than 0, that's it, we're done. Right? Okay, so maybe we don't even need that here. So that's, break or something, or return, sure. Return. So that stops the loop, stops the recursion. Otherwise, print the number and call ourselves again. So this here is the base case. If we get to less than 0, we're done. Game over. Now my recursion will work and it doesn't crash anymore. Stopped at 0. Because we're going to call ourselves. As soon as we get to less than 0, we're done. There's no longer any recursion happening. Other than that, the second thing we have to be able to identify is how do I take a complex problem and make it simpler to approach the base case? So how do I get from where I am to one step closer to making it stop? The base case here. In our case, we're just subtracting 1. That's it. So this is approaching the simplest case, approaching the base case. So if I can identify a base case, and I can take a complex problem and make it approach the base case, it might be possible to solve with recursion. A fun thing about recursion is not every problem can be solved recursively, but any problem that you can solve with recursion, you can solve without recursion, or iteratively. Right? It's the same idea here. If we define count given number, count iterative. We'll say while number is greater than 0, print number minus equals 1. Right? And actually less than or equal to 0 because we want it to print out the 0, and then we want it to stop. So this function and that function do the exact same thing, essentially. Right? They're printing numbers from the number down to 0. This one uses recursion, this one doesn't. So when you're talking about algorithms and performance and efficiency, and that's the chapter we skipped, by the way, you'll get back to that in algorithms analysis for sure. We'll do a high-level overview later as well. The iterative function is faster, uses less memory, is more efficient, because every time we recurse, what happens here, let me put a breakpoint in here, and we'll debug this here. What's going to happen is all of those function calls are going to get added up and held on to, because Python needs to know where to go back. So right now over here on the left, this is my stack, my frames. These are execution frames. And every time we step, so I'm going to step into my code over and over and over, every time we call count, we're adding another execution frame, adding to the stack. This is called the call stack. So here's a bunch of them. So here I was at count in main at line 5, and the number was 100. Here, the number was 99. Here, the number is 98 and 97. So every single time we call a function, Python needs to track what the values are of that function. So it's taking up more memory because it has to track all of these function calls. Remember, the reason is when we call a function, we jump to that part of the code. That code executes. When it's done, we come back to where we were. So when we're done, we say these are resolved or pulled off the stack. They're finished. And we go back to where we came here. Again, there's nothing to do after the fact because we just called count. But if there was something to do after, we would do some operations after the fact. Okay, sorry, this is mostly review from stuff we did in 1501. If you're new, it's a new topic, that's okay, don't worry too much about it. It's interesting, but not super critical at this point. I mean, when we get to the recursion project, it'll matter much more. So I guess it is important. Okay, so I'm just going to stop it here. So recursion is nice because sometimes it can solve problems very easily that are more difficult to solve otherwise. In this case, no, it doesn't matter. I mean, they're identical. Aside from using a little bit more memory here. But what we can do with Fibonacci is really cool. If we define our fib, and we want like the nth digit. So for a Fibonacci number, the nth digit in the Fibonacci sequence, which actually I found out rather recently. Actually, you can figure this out without doing all the previous arithmetic, but you need like some square root of 5 or something like that, and it doesn't come out pretty. But assuming we didn't know that, right? What is our base case? Our base case is, well, the first and the second value in Fibonacci are 1. So if nth equals 1 or nth equals 2, we return 1. That's it. That's the base case. That's as easy as it gets. Right? I know what the solution is. If I didn't return 1, I'm going to return fib of nth minus 1 plus fib of nth minus 2. Right? That's the mathematical definition. It's the sum of the previous 2 digits. If you want the third digit, I'm going to give you, well, the sum of the first plus the sum of the second. I'm sorry, the sum of the first and the second. Sum implies adding there. Right, so this works. This will give me the fib digits here. So let's go, I don't know, for n in range, let's just go to like 30 here. Let's print fib of n. We'll get the first 30 digits of Fibonacci here. And this is a recursive solution. Oops. Oh, okay. This is bad. We did a bad thing here. Notice it says the maximum recursion depth exceeded. Well, what happened is the first value, when I said fib of 0, oops, fib of 0 is not 1 or 2, so it kept going negative. Well, that's bad. So really, I guess what I want here is if nth is less than 2, return 1. So we'll say fib of 0 is 1 and fib of 1 is 1. Sure, why not? And notice it calculates all of our Fibonacci values. 1, 1, 2, 3, 5, 8, 13, on and on and on, up to here. Sure, that works. Now let's go, like, say to 40. Let's make my computer cry. If we want 40 values, notice it's thinking really hard about it here. It's doing it, but it's thinking really hard about it. No, it's still running. Still running. Oh my goodness. Poor computer. Because what's happening here is it has to calculate nth minus 1 all the way down until it gets a 1 and add up all those 1s together. So it has added up 1 14 million times. Nope, sorry. Yep, 14 million times. 14.9. Oh, I can zoom that, sorry. And then 24 million times we've added up the number 1. This is an incredibly slow operation, right? It's terrible. Because what's happening is when you call fib, say, I'm just going to stop it here because that's just sad. Let me draw this out because it is really fun to draw. It's fun to draw. Let this load up here. Okay. And we'll zoom this in. Okay. So fib, we'll just do like 7, right, is fib of 6 plus fib of 5. I'm just going to do f now because that's shorter. 6 is f of 5 plus f of 4. f4. 5 is 4 plus 3, right? F of 4, f of 3. 5 is f of 4 plus f of 3. 4 is f of 3 plus f of 2. Right? You see how this is just exponentially spiraling? F of 2. So on and on and on. Every one of these calls has to be added up. And the more that we do, right, the more adding we have to do, because eventually we'll get a bunch of 1s. So f of 3 is f of 1 plus f of 2. F of 2 is f of 0 plus f of 1. F of 2 is f of 0 plus f of 1. right? On and on and on, right? 3 and 2 and 2 and 1 and 1 and 0 and on and on and on and on. So this just spirals out of control. It's terribly inefficient. It's bad Fibonacci, right? Where really we could do it iteratively. I mean, we already did a progression iteratively. I guess I don't need to do that again. If you really want to use recursion, we can do that. So we're going to define a better fib here. It takes an nth. Again, we have the same base case. But now what we need to do is we need to track more information. So instead of counting from 1, we need to be working our way up. So what we do is we add a private helper method that takes a couple more values. We have the nth, we have the current nth, we have the previous, and we have the current value. Okay, so we're going to say if nth is equal to the current nth, then we're going to return previous plus current. Hope if I could spell right. Yeah, previous plus current. So in this case, if we're counting up, so we're going to go from nth of 1, nth of 2, nth of 3, nth of 4, nth of 5, nth of 6. Once we get to our target nth, I can return previous plus current because I'm going to give you those previous 2 digits. If we're not there, we return better fib of nth, current nth plus 1. The previous is the current, and the current is the previous plus the current. So we're essentially just doing a loop here. So if you're just doing a loop with recursion, it's probably better to just do a loop. Okay, and just because you can make it recursive doesn't mean it has to be. So this is going to count up for us. So if we do better fib, and again, the reason here that we do a helper method is if I want a Fibonacci nth, I shouldn't have to tell it my current and my previous and my current. Current nth, previous, and current value. I want to make a public method that's easy for them to use. So here's a public function. It can call the helper one that has all that extra details. Right? Return better fib of nth. The current is 3, previous is 1, current is 1. So my nth is still the same. So if it's not less than 2, right? I guess that would be 2 then, right? So nth. So if nth was 2, I'll give you 2 is your current, and 1 plus 1. So I can do better fib of n, and this one is fast because it's quick to add up. Still using recursion, but it's essentially just a loop. And now we get our values even faster. Right? 1, 1, 2, 3, 5, 8, 13, on and on and on, and it can add up to, was that 102 million already? Look at that, pretty quick. We stopped at 24 million, I think, or 39 million. I didn't even let it finish with the slow one. This is terribly, terribly slow and bad. Counts a bunch of 1s. Okay. How are you feeling so far? You know, this is pretty much a recap of stuff we did last semester. I apologize. On Thursday, we'll get into new stuff, and then we can start talking about the next project. And then we'll have a lab exercise on Monday where you guys get to practice one of these things. Again, not as big as the project, just a smaller practice one. You guys okay so far? Chat's been really quiet. I'm sorry. It's hard to tell sometimes when chat's quiet. Okay. It'll take some practice. I mean, yeah, I'm gonna post it all here too, so like don't feel like you have to copy it all right away. So here's Recursion with fib. Yep, if it's helpful to copy, yeah, please go ahead and follow along and shout at me if I'm going too fast, but I definitely will post it all for you after. Okay, so we'll talk more about Fibonacci. We'll look at using it for a couple applications here. I'm doing some fun backtracking. We can solve a maze, or we can solve Sudoku. We can do those sorts of things. Should be fun. when you can just type. What do you mean by when you just type? Oh, so like fib of a value is just saying I want the nth digit in Fibonacci. And what the function is doing is it's saying, okay, my base case, if I'm less than 2, it's got to be 1. For the helper function, the base case is, hey, did I reach my current nth? If I did, okay, add up previous and current. If not, all right, well, now add 1 to current, and then current is now the previous, and the previous plus the current is now the next. So our loop here, I want to print each individual value just to show you. I want fib of 0th, fib of 1th, fib of 2th, whatever, 3, like each nth of fib. So we could say like this is my n n colon, sure, something like that. Then we can see like, hey, this is the value. Here's the 0th value of Fibonacci. Nth. Here's the nth value, or nth number in the series, and here it is. So it might be missing one of these pieces here. So I was just trying to illustrate the values, like printing each one at a time. Ideally, like if someone wants a Fibonacci number, you would just calculate, hey, I just need the 15th. You wouldn't have to print out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 along the way. You would just give them the 15th. Okay, so I'll be hanging out after the fact. I'll be in Discord. I can do some office hours. If you guys have other questions, you want to drop on by. But I think that's good for today, and we're just about out of time here. So that's good. So find me there. We can chat if you have other questions, and then we'll pick it back up on Thursday. Okay, cool. Yeah, I'm glad it's working there, Eric. Yeah, no problem. All right, gang. That was fun. Let's see. Is there anyone else around? Let's see. I think we rated somebody last time, right? I don't know if yeah, not too much right now. Okay, yeah, we'll just end it here. Yeah, so office hours, right after class, I'll be in Discord, but I won't be like streaming anything for the office hours, so we can chat. All right, so just ping me on Discord or send me a direct message or find me there in the chat room for the class, and we can go from there. Hey, you guys take care.